Good afternoon. So welcome to our panel, From Chaos to Code, How AI Can Tame the Climate Crisis. As we're witnessing increasingly frequent extreme weather events, we face unprecedented challenges across interconnected systems in a complex, evolving geopolitical landscape. These climate extremes threaten cascading failures, affecting infrastructure, supply chains, healthcare, communities, and ecosystems. Today, we explore how artificial intelligence is emerging as a powerful ally in predicting, preparing for, and responding to these challenges. Our panelists bring expertise spanning climate science, infrastructure resilience, food systems, energy optimization, and ecological adaptation. The university's distinctive role in this conversation is to move beyond stage one thinking and examine the complex relationships among technology, society, and ethical considerations. Our academic perspective allows us to consider the full web of consequences, avoiding interventions that might solve immediate problems while creating more profound ones downstream. So that's why we're here. We have that capacity to think deeply about these problems and the latitude to do so. This distinguished panel helps us navigate these complexities with the nuance they deserve, drawing on diverse experience to illuminate both opportunities and challenges. Together, we'll examine how AI can help us understand climate patterns, strengthen infrastructure, secure food systems, optimize energy grids, and protect vulnerable ecosystems and communities, all while maintaining a critical perspective on the technology itself. Before we begin our panel discussion, I'd like to introduce our distinguished panelists. Adam Sobel is a professor of applied physics and applied mathematics in Columbia Engineering and a professor of earth and environmental sciences at Lamont-Doherty Earth Observatory. He studies climate and weather dynamics, particularly in the tropics, focusing on risks to society from extreme weather events. He has authored over 150 peer-reviewed articles, the book Storm Surge about Hurricane Sandy, and numerous op-eds. George Deodatis is the Santiago and Robertina Calatrava Family Professor of Civil Engineering and Earth and Environmental Engineering. He specializes in probabilistic methods for civil infrastructure systems, focusing on structural safety under natural hazards, including climate change. His contributions have been recognized with numerous awards, including Columbia University's Presidential Award for Outstanding Teaching. Jessica Fanzo, Professor of Climate and Director of the Food for Humanity Initiative at the Columbia Climate School, is the leading expert on climate change and food systems in vulnerable communities. She has served with international organizations and UN agencies, advised governments on food security, led global policy initiatives, authored books on food systems, and was elected to the National Academy of Sciences in 2024. Bolun is an assistant professor of earth and environmental engineering, specializing in sustainable energy systems and decarbonization. His research focuses on energy planning, electricity markets for renewables, and distributed energy resources, drawing on expertise from Shanghai Jiao Tong University, ETH Zurich, University of Washington, and MIT. Dustin Rubenstein is a professor of ecology, evolution, and environmental biology, researching animal societies and adaptation to environmental change. An award-winning scientist with over 125 publications, he has studied species across 6 continents and has been recognized by the National Academy of Sciences and Columbia University for his research and teaching contributions. Each of these experts brings a unique perspective to using AI for climate challenges. Together, they'll help us understand both the technical opportunities and human dimensions of this critical intersection. But first, David Sandalo will provide introductory remarks as lead author of the recent Artificial Intelligence for Climate Change Mitigation Roadmap. David is the inaugural fellow at the Center on Global Energy Policy and co-director of Energy and Environment at Columbia's School of International and Public Affairs. He has served in senior roles at the White House, State Department, and Department of Energy, written extensively on energy policy, and led key research on AI for climate change mitigation. He is also a distinguished research professor at the Oxford Institute for Energy Studies and Council on Foreign Relations member. So welcome, David.
Thank you, Michael, and congratulations to the organizers of this terrific conference. The CEO of a major environmental group approached me at a public event recently and asked me, AI, good or bad? Now, I teach my students that brevity can be a powerful form of communication, so in many ways I admired the simplicity of that question. And after reflection, my answer was, AI is good and bad. AI is a tool, and like a hammer can build buildings and fix furniture, but it can also break windows and hurt people. And AI can help us cure diseases, it can teach children around the world, it can help us fight climate change, but AI can also help create bioweapons, it can spread disinformation, and it can make it cheaper to pollute. So AI can be both good or bad, and the focus of much of my work for the past couple of years has been to identify the ways that AI can help us fight climate change and then try to figure out what the barriers are to those ways and mobilize colleagues to use AI to help fight climate change. And along with a great team of co-authors, we put out the book that Michael referred to. It's called The Artificial Intelligence for Climate Change Mitigation Roadmap. Maybe we should come up with a catchier title. But it's got 17 chapters and 334 pages answering these questions. And you can download it. Actually, you can download the entire PDF, or you can download individual chapters on a number of different websites. Or you can buy it on Amazon as well if you want a hard copy version. And the basic message of our roadmap is that AI has the potential to do lots of good things to fight climate change. And we divide that into two categories, roughly: incremental gains and transformational gains. And to summarize in 2 minutes what we say in 334 pages, examples of incremental gains are, for example, using AI to improve the productivity of solar and wind farms. This is already happening. AI can be a very good tool for predicting weather patterns. AI can predict weather. Modern ML tools can actually predict weather patterns more cheaply with less energy than conventional weather prediction. And when you predict solar and wind patterns better, you get more productivity out of wind farms and solar farms, for example, when you can pivot the solar and wind turbines towards the resource, or you can match the resource with the electric grid. And we're already seeing that. 10, 15, 20% improvement of productivity in wind farms using AI and ML tools. Same thing is true with incremental gains in building energy efficiency. We have lots of data about the way people use buildings, and you can use machine learning tools if you've got the right data to improve the energy efficiency of buildings. And these 10, 15, 20% incremental gains add up and potentially can be pretty significant in the fight against climate change. But beyond that, I think I'm even more excited for the potential for transformational gains from AI. And there are a number of different transformational gains that are possible. One that I'm particularly excited about is in materials innovation. We need all kinds of innovations in different materials to help fight climate change. For example, I remember when I served at the Department of Energy. When I arrived there in 2009, I was briefed by a team there that told me offshore wind would never really work, they said, because the steel that you would use in turbines is too corrosive for the marine environment, and it's too heavy. And innovations in making durable, lightweight, non-corrosive steel have helped us make offshore wind into a reality. And we need lots of innovations like that to get emissions down. Now, famously, 150 years ago, when Thomas Edison invented the modern light bulb, he spent months and months and months physically testing different types of elements or materials, running electricity through them to see how much light and heat would be produced, and he finally came up with what he thought was the optimal solution. Today, we can simulate 1 million of those interactions in a second, and using modern AI tools. And that ability gives us, actually, it's two benefits. One of them is we can test materials that don't actually exist, and then if it looks like they would be beneficial in a certain application, we can fabricate them and see whether they do work. And then we can down select much more quickly. So the potential for AI to help us accelerate the pace of energy innovation, I think, is outsized. And we need to figure out how to mobilize all kinds of tools to do that. I mean, just digital twinning technologies, and also, actually, by the way, just using large language models to take 2,000 articles in the scientific literature about a certain material and synthesize it more quickly can make a big difference. So I think AI has lots of potential to do good things, but it also has potential to cause big problems, and that's something we need to address. One topic that's gotten a lot of attention lately is the amount of power that AI uses. This is the hot topic in every energy conference I go to, is how much power AI is using. And of course, all that power can cause greenhouse gas emissions, which could be a big problem. And that's something we need to be paying attention to. We need to pay close attention to it, although I think in some ways it's gotten more attention than it merits, because even in the most, so today about 1.52% of electricity in the US is used by data centers. There are projections that could go up to 6 or 10%. That means 90% of the electricity used will not be used for data centers. And electricity is only half of our primary energy. And so, ballpark, 95% of the energy in the United States, even under the most aggressive scenarios for growth of data centers, is not going to go into powering data centers. So I think if we use AI right, we could hopefully make improvements in the other 95% of energy that would contain any increase in emissions from data centers. But that won't happen unless we work at it. So I'm going to wrap up with 3 specific recommendations. We have lots of recommendations we have literally hundreds of recommendations in our book for specific actions people can take. Here are some that I think are important. First, we need to find ways to bring the AI and climate communities together. I found it's very interesting how there are a lot of people who know about AI who would like to work on climate but don't know anything about climate or very little. And there are people who know about climate that don't know about AI. We need to bring those communities together to come up with the best solutions. This conference is a great example in that. Then we need to invest heavily in AI for breakthrough energy solutions of the type I was talking about. And then I think we need to require disclosure of greenhouse gas emissions that come from data centers and the AI models. There's a long experience in US environmental regulation of disclosure helping drive very positive behavior. And I think disclosure obligations would make a big difference. If you're interested in any of this, I just launched a podcast on this topic. It's the AI, Energy, and Climate Podcast. You can listen on Apple, Spotify, everywhere. The AI, Energy, and Climate Podcast. We just had a great guest yesterday, a former commissioner of the Federal Communications Commission, who spoke about the dawn of the internet era and compared that to what's happening today. So if you're interested, please come listen to the AI, Energy, and Climate Podcast. So AI, good or bad? It's going to be both. It's up to us to make the best decisions to make sure that AI's impact is as good as possible. Thank you.
Thank you, David. I'd like to invite the panelists up, and that was a perfect introduction. It was exactly the nuance we were looking for, and we hope to provide some more nuance and try to understand the good and bad potential for AI. Thanks, everyone. So we have a few different sections here that we'll be talking about. And our first section is trying to understand climate challenges, where we're going to establish the foundations of climate challenges that AI might help us address. So Adam, could you start us off by discussing what's happening with AI weather models today? How is this technology changing our ability to predict weather patterns and extreme events?
Yeah, it's really been astonishing in the last few years. And I should say I haven't worked on this myself, but I know a lot of people that do, and I've tried to follow what's happening. So first we should understand the way weather is normally forecast, or was as of 5 years ago, and still to some degree is, which is that we have observations, we have satellites and weather balloons, and we see what the weather's doing today, and then to see what it's doing in the future, we take all that data and feed it into weather prediction models, which are based on physics. Historically, and so they're solving partial differential equations. I teach about them in my classes, and they march forward in time as close as they can be. There's always approximations and shortcuts, but as close as they can to the equations of physics, and you have to do it many times because of chaos. Little errors grow, and there's a whole science of weather prediction that's evolved since the 1940s, really, and 50s using digital computers. What's happened now is that the AI models, which essentially didn't exist something like 5 years ago, have become as good by many metrics, or even arguably better by some, than the physics-based models. So the AI models don't know more or less anything about the physics of the atmosphere explicitly. They don't know about conservation of energy or momentum or any of that. They're given, just like all other AI, they're trained on data. So you give them lots of historical weather data, and by knowing what happened in the past and then seeing what happened later, they find the patterns, the way that, the mysterious way that machine learning and AI do, and they step forward. And so that, as with other AI, the training is very expensive, but the forecasting, as David said, the actual running of the models in real time is very cheap, and they've gone just from nowhere to being really, really powerful in a short time. And so all the major weather centers of the world are now, or at least the most important ones are investing in this technology. It's worth saying that they're still dependent on the traditional system because all the data that's fed into them, both for training and for initialization, for giving them their starting point for each forecast, comes still from the traditional system, which uses physics-based models to sort of integrate the so-called assimilate the observations and create a usable initial state. So the AI can't do the whole job on its own, although I expect that those problems are probably solvable, and AI will be able to eventually do it with just the observations that you won't need physics at all. We may still want the physics models for all kinds of reasons. The other thing to say is that climate prediction is different, especially long-term climate prediction, prediction of climate change, because where we have, it's a much harder problem for AI that hasn't been solved, because where we have many, 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 many samples of weather for training data, we don't have many samples of climate. We don't have lots of observations of climates with different amounts of CO2 in the atmosphere, and so it's a much harder problem, and AI has to be, people are working on it, but you have to combine it with physics and try different things. So that's, so it's just, it's just really been amazing how fast it's happened.
Thanks, Adam. And that's so basically a rapid transformation, really, of our capabilities around weather prediction. So now, George, one significant way AI might contribute to civil engineering, so this is more of an application, is through improved extreme event predictions. So why are more accurate forecasts of hazards like severe storms, coastal surges, extreme winds so critical for infrastructure resilience?
We all saw what happened to our infrastructure after Hurricane Sandy. It was something that was not anticipated, and there's something that we have to do in order to increase the resilience of our built infrastructure. So what do we have to do in order to adapt our infrastructure to the detrimental consequences of weather-related and climate-related hazards, including sea level rise? And at the same time, of course, increase the resilience of the infrastructure. The answer is we have to do a risk assessment and risk management studies of geographical areas under high risk. And risk in general is a function, depends on 4 components. The hazard, obviously. The exposure, this means the assets under consideration. This can be the infrastructure, the economy of an area, the environment, the population, and so on. The vulnerability of our assets, and of course, the resilience of the assets. So the hazard component has a lot of uncertainty. We all know that predicting a hurricane, especially as far as climate is concerned, when is a hurricane gonna happen over the next 5 years, 10 years, 20 years? What is the frequency and the anticipated intensity is very tough. And so far, we have some models, probabilistic models, describing this uncertainty. But these models are assuming a stationary climate, a climate that is not changing. And we know now that climate is clearly changing. So these models now, these probabilistic models about extreme events are going to be changing in time. So this makes the problem an order of magnitude more challenging, as Adam just mentioned. So we are relying on artificial intelligence approaches in order to establish in the near future some models being able to quantify in a probabilistic way this evolution of the occurrence and the intensity of these extreme events.
That's perfect. And then this brings us to Jessica's. Our food systems are like infrastructure, except they're a little bit more complex in some ways. So Jessica, could you address the specific vulnerabilities that food systems in a climate challenge community face? And maybe what cascading effects do we see when climate disasters disrupt food production and distribution?
Yeah, so I think right now we're dealing with a very fragile, global, but very connected food system. The food system is also bringing about this paradox where we have about 10% of the world's population who go to bed hungry and about 2.2 billion people who are overweight or obese. So the food system is delivering very differently depending on who you are, where you live, what kind of food you get access to. And with all of these extreme weather events, political shocks, geopolitics, it's worsening this malnutrition crisis that we see. And there's a whole range of challenges, from agriculture production to land use change, agriculture being the largest driver of deforestation in the world. Food trade flow disruptions, as Michael knows very well, that's his area of work. All the way down to people's ability to access food, either economically or physically. So this is all having ramifications, and we see this in real time in many places in the world. And you can imagine technology being really important to try to address some of these disruptions and allow for food systems to be more resilient. AI is only one tool in the toolbox. We need a lot of tools to transform our food systems. And I'm happy to talk about where AI is going in food. But I think one of the most vulnerable aspects of food systems is really in places like, and some of the people on this panel work in this region of sub-Saharan Africa, South Asia, where you're really feeling those effects of climate and extreme events on people's ability to access healthy diets, basic calories. And so there's a lot that we can do in the food world, and food data, getting access to that data and putting it in front of policymakers is critical, but we have a lot of limitations, and this is where AI can come in. Perfect. And so I guess that this, it's very brief, but we tried to understand a bit about the climate challenge. So next, I want to think about sort of applications and opportunities. And Bolun, could you discuss the current and emerging AI applications in energy system planning for resilience, and how is AI helping us to prepare our energy infrastructure for climate extremes?
Yes, Alex. So I think the first opportunity is about generating future scenarios for planning. So I think Adam put, and Adam George mentioned that because it's very hard to predict the future over the next 10 or 20 years, right? Because the weather, we have climate change, and it's not stationary. So instead of trying to predict one possibility, we want to generate, say, 100 different possibilities over the future, like what might happen in the next 20 years in terms of temperature, wind, solar, and electricity demand. Okay. But to put those information to help us to plan the energy system, we need a scenario. And particularly in the power system planning, we want high resolution scenarios. That's usually hourly resolution in time and maybe 10 square kilometer resolution in space. So you think about Texas, like we want to generate hourly resolution and 10 square meter resolution scenario over the next 20 years and give it 100 scenarios. yeah, this is a very critical challenge and a significant scale up in terms of complexity from many of the climate models. Okay, and then once you have those scenarios, say 100 possible scenarios over the entire Texas, over that resolution, feed those scenarios into the planning model. We are then looking at a significantly complex optimization and planning model that we want to find the best planning of the infrastructure. And then there's even another layer of complexity that maybe the planning to follow the local regulatory requirements. For example, in power system, the minimum requirement is this N-1, that any component in the system breaks should not affect the security of the rest of the system, though there's another combinatory of complexity added. So you see this is a very challenging problem, and AI is showing a lot of promise in helping us to, of course, scaling up from the climate model to generate those scenarios, and again, helping us to solve those highly complex optimization problems.
Oh, perfect, and I think maybe you've noticed there's sort of this common theme of developing future scenarios, and I think we could all go about thinking about, oh, maybe there's a limited number, but to do that in an efficient, quick way is challenging, and that's where AI is coming in for food systems, energy systems, infrastructure, to develop those scenarios rapidly. And Dustin, probably the same for ecosystems or ecological perspective. And so, to ask on your expertise, how might AI help organismal responses to climate change, and maybe sort of a follow on what types of species or ecosystems might benefit most from AI-driven predictions?
I think it's worth recognizing that ecology is a messy field compared to many of its lab biological sciences, right? If you've ever done field work, you get dirty, you fall off trees, you fall off rocks, you get stung by insects. So collecting the data is hard. And ecology is also complex. Ecosystems contain communities of organisms. So there's communities of birds, communities of trees, microorganisms, all interacting, all in one location, and responding to different inputs from the soil, from nutrients, from water, from temperature. And so as you perturb that system, you often get unexpected and nonlinear responses. And so at a simple level, AI tools might help us better analyze those data and make predictions under future climate change scenarios, land use change scenarios. So that's the obvious answer. But what really excites me is how we can use AI to generate new data at scales and resolutions that we couldn't probably before, or at least took a lot of work and cost a lot of money. So the obvious example there is using satellite imagery, right? At the ecosystem level, we have newer satellites. We can identify individual tree species. We can tell when they're fruiting, when they're leafing out, on spatial scales and temporal scales that we couldn't before. In fact, I think the use of images from computer science is transforming all scales of ecology. The ability to identify species is a relatively mature technology, right? So if you pull out your phone, you may have an app, a Merlin app, that may allow you to identify birdsong by just recording it. Or there's a suite of apps that you can take a picture and it'll tell you what species of tree or what species of animal that is. In fact, if you have an iPhone, that's now built into the operating system. And if you open your Photos app and look at a picture of a bird, the Apple Intelligence will take a guess and tell you what species that is. So that's quite mature. But as a behavioral ecologist, I'm very interested in how individual organisms respond to environmental change. And I think to start to make real predictions, we need to understand variation at the individual level to be able to predict what populations and what ecosystems are going to do in response to climate change or land use change. And I think that's where the same technology can be very useful. We're moving from individual species recognition to individual identification using images from camera traps or from recording pods. And so we can record individual variation in the notes of the bird song, for example, when images might not work. Or we can use images to capture individual zebras. I think that was the first species because they have almost a barcode, like a fingerprint. And you can make really good population projections and follow those animals and see where they go to be able to see what happens during droughts or periods of land use change. And I think now we're up to about 55 species from camera trap images that we can identify individually. That's going to jump to probably 75 or 80 this year. We can do most As I said, most birds by species, and there are a few species where we're starting to use that information. So I think as we move to projections, we can scale up from actual individual level variation and differences up to populations, up to ecosystems, and make much better projections of how organisms are going to respond to change.
Oh, that was really great. I don't know if there's an analogy to go back to insurance, but maybe you could think of something, Adam. How is the insurance industry adapting its risk models to climate change, and what roles do you see for AI in building climate resilience? Maybe some behavioral connection that the insurance industry might use.
Yeah, I don't know if I can draw a connection to ecology, but thanks. So Mike is asking me this because our group works with the insurance industry on extreme weather. So in insurance, and insurance is really where the rubber is hitting the road first, and I would say in terms of climate impacts on the US economy, as you may know, insurers are having trouble operating in the states where the weather risks are highest. So what we mean by risk is we're not talking about the events. The insurance industry isn't insuring against things happening in the next few days where you could actually do a forecast. They need to know the probabilities of events that have big consequences, far enough in the future that you can't predict them, but you want to know the probabilities so you know how to price insurance. And disasters, this is particularly tricky because most of the losses from disasters are from a few big events, and so there's not that many of them to count. So if you health insurance or life insurance, we have lots of data on individuals that are uncorrelated, and so you can know how to price insurance. That's what actuaries do. But disasters, there's only a few, and each one does a lot of damage. So there aren't enough in the historical record to sort of estimate the risk just by counting the ones that happened before. So the insurance industry has developed its own science to do this, and they use what's called catastrophe models, which sort of generate artificial histories that are sort of like the real history but have more of the gaps filled in so that they can estimate the probabilities more or less empirically of different types of hurricanes, fires, floods, et cetera, as well as their consequences, and that's what's used to price contracts for insurance and reinsurance. So the science of catastrophe models is pretty, it's distinct, connected to the science of weather and climate prediction, but distinct. It's traditionally pretty empirical, pretty data driven. So AI is kind of a natural thing to use there. And I believe it is already being used by the companies that do this research, which so-called catastrophe model vendors that serve the insurance industry, and we work with some of them. I don't understand the details of what people are doing, but there is a lot of, you have past events, and then you want to know the probabilities, and you have to model not only the probabilities of the events, but their details. What will the wind footprint be of a hurricane? What will the extent of a fire be? So the limitation is training data always, having enough data, and especially data on actual financial losses, which is part of the equation, is proprietary and never enough of it. Data on the assets, the building stock if you're doing property insurance. But I think this is a natural area where we're going to see, and already are seeing, substantial use of AI.
Thanks, Adam. When you said catastrophe model, my mind immediately jumped, maybe there is some ecosystem connection or food system connection. So, which actually brings us to our next section is on interdisciplinary connections. And George, so I was thinking then, so how do you improve AI, how do improved AI forecasts for extreme weather feed into your risk assessment process? And I guess the question, would better prediction of hurricane intensity or flooding affect how you set safety margins or update building codes? So that intersection there.
As I mentioned, risk has 4 components. It's the hazard, the exposure, the assets, and then vulnerability and resilience. And I talked about how AI can help us with quantifying the hazard. Now, there are a lot of exciting new techniques, including remote sensing, satellite imaging, drone photography, LiDAR, and several other techniques that have been introduced over the last 10, 15, 20 years that are helping us in combination with data science approaches, AI and ML, in order to have a very accurate description of the assets involved. And then the same technologies, again, in combination with artificial intelligence and machine learning techniques, can help us better quantify the last 2 components, of the equation: the vulnerability of the assets and the resilience of the assets. But where AI is going to be even more critical is in integrating the four components, which is most probably the most challenging part of the entire problem.
And yeah, I guess on this integration point, this is really critical for food systems. And Jess, so maybe the question, what AI applications are emerging in food security and nutrition during climate disasters? How might AI help coordinate responses across sectors, and which requires integration? Thoughts on that?
So I think AI can be important, and a lot of this is being piloted or tested. It's not at scale for in the food system world. I mean, there's predictive capabilities, things like genetics, phenotyping for plant breeding, being able to evaluate nutrient and water demands, monitoring biotic and abiotic stresses with crops and livestock, being able to monitor pathogens. All of these are being tested to really bring out predictive capabilities. Obviously, following food flows, food shocks, being able to track and trace food to minimize disruption, all the way to personalized nutrition. Again, an app on your phone where you can plug in a bit of data and it can feed you better health information. I think a lot of this is in the works. There's most of what you see is in the ag side on farms using weather data, using a lot of the technologies that George had alluded to, remote sensing, et cetera, to better predict in a climate scenario what kind of crops, what kind of soil, what kind of inputs do you need to be able to ensure that you have yields. So I think that's the majority. Where the integration piece comes in, those that work on long-term climate change and understand and forecast versus those who are looking at near-term extreme events versus those who are measuring food security and nutrition outcomes in the field. These are very different methodologies, ways of doing research, and bringing that together to be able to understand how will an extreme event impact someone's food security, their biological health outcomes. It is very difficult to bring that kind of data together and make sense of it and think about causation. So AI could potentially help in bridging those very disparate methodologies across the different scientific disciplines. I just want to add two other things, Michael, if you give me permission. In the food world, we have a lot of historical technologies. And it's not so much that it's a failure of technology, but are we able to anticipate and account for the impacts of that technology? If you look at food systems, you see a lot of inequities. Smallholder farmers, indigenous populations, and peoples who very much shepherd and are the custodians of ecosystems and our food systems are often left behind in this race towards better data and decision making. So I think we have to be very careful about how we employ these technologies, particularly because we have so many smallholder farmers in the world that are often being left behind. So this data democratization around AI is going to be so important. And just can I say one last thing?
Please.
We have something called the Global Food Systems Dashboard. Michael works on it with me. It's a very large collaboration with multiple partners. It took us about 4 years to develop this dashboard, and it brings together a ton of data across food systems and presents it in very visually appealing ways for the non-researcher, more of the politician person in mind. And this took a long time and about $2 million to put together this dashboard. And one of my colleagues who works on the dashboard fed it our metadata to ChatGPT and asked to design a dashboard. And it did it in like 30 minutes. And then the dashboard was actually much nicer and much more user-friendly. It was hilarious, but what took us, almost 4 or 5 years to develop with a lot of money and person power took AI, 30 minutes. So it's quite incredible of the speed of this. Again, though, the speed being potentially a constraint for a lot of populations to be able to grasp that speed and take up that technology and use it effectively.
That's so important, that speed of integration, which we're trying to integrate. But you also said something about inequality, and that's another, I think, common theme cutting across our different topics. And Bolun, even for energy systems, right? We have to think about inequality. So I think it's an important aspect. But to bring it back, so Bolun, what role can AI play in optimizing energy systems during extreme events? And how can it balance immediate needs with long-term resilience? And again, there is that equality aspect that we have to keep in mind too.
Yeah, exactly. So during the extreme event, if you think about energy system, basically we are thinking about two measures, identification and isolation. Identification is you want to understand what's happening to the system, if you have a fault, wildfire, lightning strike, etc. And then isolation is we want to contain the fault or an area and isolate it, minimizing the negative impact and keep the system resident in running. Okay, so AI obviously is already making a lot of impact on the monitoring. So with satellite imaging, camera, or even drone. AI can basically perform in the background monitoring conditions in the system, such as quickly identifying potential wildfires and then quickly, or extreme weather, and quickly assessing the consequenting impact and making recommendations to the power system operator. So in this case, I think AI is already making a significant difference in power system operation. And then in terms of isolation or treatment, I think, Michael, as you mentioned, equality is a critical impact because in the past, when power system operator have problem, and this is exactly what happened in 2021 during the winter storm Uri, when they see the problem, that means we cannot supply enough demand, and then we need to cut off demand. So I think during that time, Texas cut off around 30% of the demand because we lost a lot of generation, so can keep rest of the system to keep performing. But if you think about a system which is basically a network structure, right? If you have a branching structure, then the easiest way you cut off demand is you cut off the branches. Okay, but it's usually or historically more disadvantaged communities live in the branched area, which has usually have a less up-to-date infrastructure. So if you simply considering from how do we minimize the effort to keep the system running, we usually will cut off the branching load, and often cases that's kind of disadvantaged communities. But on the other hand, with new deployments of battery, solar PV, we are seeing our affluent neighborhoods are deploying microgrids. That's like a Tesla Powerwall that you can supply your home. So this really is this interesting development that we should rethink about how we cut off demand in terms of emergency, and taking consideration that some families or some buildings, they can supply themselves through the microgrid, while we have also disadvantaged communities. So I think those cases, AI can help a lot with making recommendations and sometimes even simulating different scenarios, making quick decisions, performing in the background, and making recommendations to the power system operators. Those are really, I think, what AI is already showing a lot of promises. Yeah.
That's fascinating. You mentioned about networks and fairness and equality. I mean, these are really challenging but key concepts. Bring us back to the ecosystems, Dustin, like conservation efforts often cross multiple disciplines. So a question, how might AI tools that predict animal and plant responses to climate change inform work with urban planners, agricultural scientists or disaster teams. What benefit are you seeing in having some of this cross-collaboration?
I think as we move to studying more diverse sets of species, we need to be working with park managers and people that are protecting species. There's actually a need for that. There's faculty here at Columbia that are looking at poaching in Africa and trying to use machine learning to study the areas, the times of year, and the times of day when poachers were predicted to attack animals for bushmeat. And this has proven successful, and other park managers from around the world are reaching out to work with the computer scientists to adopt those sorts of models. And all of this, it relies on the training data and making data available. And I think that's where partnerships are going to be really important. One area that has seen growth over the last decade or so is tracking animals, partly because it used to be you could put a GPS tag on an elephant, because GPSs were big and the batteries were big, but that technology has shrunk. And now we can put it on much smaller animals, medium-sized and small animals. And so as we make that data available, who should those data be available to, right? If you put it on an endangered species and you make the GPS coordinates available to everybody, that may not be the best thing. So it's working with conservation managers, conservation planners about what data to make available, how to make the data available. On one scale, we need those data to be able to train the models, but then what do you do with those data? So I think as you see animal movements in particular relate to urban planning, where you set up farms, where you pull down fences and things like that. And so as we look for these patterns, those types of relationships are really important.
Great. I think we could talk for a week on this. We could for sure. But we only have a few minutes left, and we're at our sort of final section. And this was on future directions and challenges. Maybe since we don't have much time, I'll just ask the panelists for one of the key challenges that you see with AI. So Adam, we could start with you. So when thinking about AI transformation as a tool, especially for risk assessment and insurance, what type of pitfalls do you see, what concerns you most?
And actually, if it's okay, I'd like to answer it in the context of weather rather than insurance, because it's really very timely. So I think, as with a lot of AI things, it's the thing I worry about the most is understanding what it's doing and preventing bad outcomes from not understanding what it's doing. And the technology is moving so fast, it's really quite, problems are really quite possible. The traditional weather forecasters, as the models have gotten better and better, the human forecaster has less and less of a job. But when there's an extreme event that's really dangerous, you really need the human forecaster to interpret the different possibilities and the uncertainties and tell people what to do. And the forecasters are traditionally very conservative about bringing new technology. When the models get better, they want to test it for a long time, make sure they understand it before making it operational, and always the forecaster's there to interpret it. With AI moving so fast, there's potential to use things that people don't understand. And I think there's also a tension now between public and private, because there's a move now from the White House to privatize the Weather Service, which has been talked about for years, but there's now a real threat of it happening. And the private weather sector is still, although the AI models come from the private sector, which is a new thing. All the old weather models came from the public sector. The new stuff comes from the private sector, but it's still totally dependent on the public sector infrastructure for the underlying data and the physics models that do a lot of the background work, even if you want to use AI. So there's just a great tension here, and I think a real danger of breaking things that are in the infrastructure that we depend on to keep people safe.
That's a great point. And I think, George, maybe you might see some similar concerns around, say, infrastructure engineering, structural engineering.
Yeah, absolutely. Look, this is a truly unique opportunity with the help of AI to establish methodologies in order to determine optimal adaptation and resilience strategies for the infrastructure against weather and climate-related hazards. The problem is extremely challenging. It is highly multidisciplinary. It will involve contributions from engineering, from the physical science, from social sciences, and many other fields. And the only way to approach it is through a novel Monte Carlo approach, including stochastic optimization. AI, again, is going to help us with integrating all these different disciplines, contributing to the eventual solution of the problem.
Perfect. And Justin, for around food systems, the ethical concerns, or what if there's some
There's
other...
a lot of ethical concerns that we don't have time for. But I think inclusive decision making is important. The design, the development, the deployment of the data, who's involved in that, who's making those decisions, who has ownership of that data. In food systems, we have tons of data gaps. We don't really understand who's deeply food insecure beyond urban, rural, men, women, really crude ways of disaggregation. And AI might not solve all those data gaps, and we still need the human piece, and Adam had talked about that. We need humans working hand in hand with AI. Of course, we've got about 1.5 billion people who work formally in the food system. If robotics and other technologies take over, what are we gaining? What are we losing from a labor perspective, from an economy perspective? So lots of hard answers, lots of hard questions that are really relevant to people who are at the center of food systems that we need to be thinking about.
Perfect. And Bolun, maybe 30 seconds, what are the biggest concerns for energy systems?
Yeah, I think one particular angle that's closest to my research is energy storage operation. So let's think about California. I think 30% of capacity now are giant batteries in California. And it's fair to say that many of those batteries are actually now operated by AI, of course with human monitoring, but their market action, their market offers are generated by AI. And in many cases, we cannot explain them. And so we are seeing some confusing actions of battery in the AI, and it's especially making the power system operator worries. And so it's really about understanding and the transparency and how to regulate this AI. And I think that's a real concern now with many power system operators. Yeah.
Okay. Well, Dustin, just very quickly, I mean, what's your biggest concern, just in a couple of words?
I think we know that the models rely on the data we train them with. And I think most people here are talking about one species, humans, and what happens when we train our models for one species or one family of species, and then do we cut corners and try to use that to project with other species? I think that's a real concern. How much can we refine our models to be able to work on another ecosystem and other species when the training data are from something different?
Well, I mean, I love this. I mean, I could talk about this all day with all of you. This is wonderful. So thank you to all our panelists, and thank you everyone for joining us. There's a QR code on the screen that allows you to submit, or maybe there will be, submit questions. So we didn't have time for questions here, but I hope you enjoyed, and thanks for coming. Thank you, everyone.